see how this one goes. So we're gonna separate as we drew, right? So when we drew this thing, we had copper as a solid. We're gonna do separate everything as it truly happens. That's not how we normally write the reactions, but we're gonna separate it. Now, what did we have? How many silver ions did we have?
2.
So I have 2 silver ions, and they're gonna be aqueous. And I'm gonna have 2 nitrate ions, because that's what you really had when we did the drawing, right? And that's gonna be aqueous. Ions are always aqueous if you have them like that. If they're separated. If it were a solid, it wouldn't separate, right? But this is aqueous, which means it is separated. You have 2 silvers and you have 2 nitrates in the solution. And then at the end, we had how many coppers? 1 copper 2 plus. That was aqueous. How many nitrates did I have? 2 NO3 minuses. Those are aqueous as well. And I was at the end, how many silvers did I have? 2 Ags, and these were solids. This is called the complete ionic equation. Yes?
Because there's a 2 under the nitrate, like on the top, does it not mean that there's 2 coppers?
What this means is that copper has a 2 plus charge. This is a minus charge. So this 2 tells me that that's a 2 plus charge if we're using that trick.
What is this called?
Complete ionic equation.
Oh, so the subscript only has to do with 1, but if it has a coefficient, then it has to do with the whole molecule?
Yes, yes. That's the complete ionic equation. Why? Because I'm writing the whole equation and I'm separating the things that can be separated into ions. So they call it a complete ionic equation. And yes, the 2 affects both of them, but if I have something in a parenthesis, the 2 affects the silver and the nitrate, but this only affects whatever is inside that parenthesis. So you have 2 nitrogens and 6 oxygens, right? The 2 does not affect the copper because this is outside the parenthesis just for that. Okay with that?
So you write it like that because those are the separated ions?
Yeah, so if I wanted to write what we really have, what I really have in here is not silver nitrate. I have silver and nitrate ions. So if I want to write it how it truly is, it's silver ions and nitrate ions, and they're separated, right? If it's aqueous, that means that you have to have them separated. Now the net ionic equation, which is what I was telling you some people prefer, net ionic equation. Net ionic equation, I'm only going to write what actually did anything because people don't want to see all the other stuff. What didn't do anything, Marshall? Which ones were your spectator ions? So I get rid of those. Anything that is exactly the same, phase the same, is aqueous, is 2, exactly the same. And it never did a thing. You get rid of those. And you only actually write what did anything. So you will write the copper as a solid. You'll write the 2 Ag pluses, aqueous. These were your reactants. And then in your products, you have the copper change from no charge to a +2 charge. So you have your copper 2 plus, which is aqueous. You see, that was solid. This is aqueous. So yes, I just have one copper, but it changed from solid and it jumped into the water. And then I have plus 2 Ags. That is how sometimes you'll see an equation. And when you see that, when you see these ions like that, it's because they're only showing you what actually reacted. The copper and the silver, you had copper and silver ions totally happy with noble gas configuration. These were very unhappy. Now the copper, according to a series that I'm going to show you in a minute, has more energy than the silver, so it will give these electrons to the silver, and now you're going to see it in solution, and the silvers came out of solution. So this is what actually happened. That's your net ionic equation.
So the net ionic equation is what changed.
What changed, yes. In any reaction, we're going to go to double displacement in a minute, and we're going to see what changed in a double displacement reaction as well. So what changes is what you write, because sometimes the equations are so big and all that fluff just makes it more confusing. So people are like, okay, what's truly happening here? And you only write what truly happens. You don't put all the other fluff that didn't do anything. Yes?
Is silver nitrate and copper nitrate, are they only ever like together in a
Well, there were ions in solution, and then there are ions in solution. To get rid of those solutions, what do I do? Evaporate the water, and then you end up with
is
the...
that ever solid? Like those two can be solid
Not when they are in solution. That's where they want to be.
without solutions?
Without the solution, the positives and the negatives will attract and come out, and it'll become a solid, and you'll end up with a salt. You get rid of all the water, they will go back, and they will have an ionic bond, and you'll have your salts. Because you can recognize that as metal and non-metal, right? So that could make a salt. Although the salt that you will make will be the copper nitrate, because they have a greater affinity. And as the copper goes into solution, and the silver will just, what would you have if you were to put this solution, and I didn't think about it, but what would you have if you were to put these products and evaporate all the water? What would you end up with? Silver and copper nitrate, right? Without the, yeah, you'll end up with two things. You'll have a salt, and then you have some silver specks throughout, right? You'll have them both. Everybody okay with this?